let's continue exploring the concept of electric flux, and let's imagine that we have a particle of charge Q naught located there, and that we want to evaluate the flux, the electric flux through, let's say, a cube over here of side L. Okay, so here we have our cube. So the electric field produced by this charged particle diverges radially away, so my arrows get smaller, and so there are electric field arrows on the sides of the cube. So if I draw them here, I'll get something that looks like that. I think I'm bending too much there, but more or less, I don't care about the electric fields over here so much. They're actually not at all, because they don't affect, they don't make contact with the cube, so they don't enter into the calculation for flux. But let's just draw them. Let's draw a few of them to illustrate the geometry of the electric field, which diverges radially away from charged particles. So what we want to do, of course, is to evaluate the integral of the electric field over all 6 sides of the cube. And so let's indicate that that's the cube, or integrate that over the cube. And so this looks like a pretty complicated calculation, right? So I have field lines here that are entering the cube, and over on this side they're exiting the cube. If I draw my dAs, right, so these are the dAs that are normal to the surface. Here my dA is pointing that way, right? That's normal to the surface. Here my dA is pointing, I guess it depends on where we are, but if this is on the top here, then the dA is still pointing upwards. If we're on the other side here, the dA is pointing there in the same direction as the electric field. Here it's sort of pointing in that direction, but there's probably some angle there. But the dAs on this side are all just normal to that other side. And here we have dAs pointing directly the opposite direction of the electric field. And some places will have an angle. So like right here, the electric field is coming in it's not exactly normal to the surface, but the dA is normal to the surface. So it looks like a pretty complicated calculation. There are places where dA dot E is 0, places where it's negative 1, where the cosine of the angle is 0, like here. And here there are places where the cosine of the angle gives us -1. And on this side there are places where we get 1. And so it looks like a pretty complicated calculation. But of course Gauss's law comes to the rescue here, because the electric flux through the cube is equivalent to finding the electric flux through a closed surface, because the cube is a closed surface, and therefore Gauss's law applies. I don't have to do a complicated calculation that involves the electric field. I simply have to look to see if the charge, or how much charge is inside, and so I look inside my closed surface and I don't see any charge, so I know that the electric flux through there is 0. And in some sense we can sort of see that we have some positive contributions from the sides over here, and there must be equal and opposite negative contributions from this side. The electric field comes in somewhere and comes out somewhere else, and the total must add to 0. Okay, so let's think about how to get a non-zero electric flux through the cube. So if I draw my cube down here, side L, and now I want to place my charged particle inside the cube, but let's say I place it not right in the middle, but somewhere over there. So that's Q naught, and it produces an electric field, which, given that I want to integrate over the surface, let's just draw it on the sides. So the electric field there is pointing that way. Over here, it's pointing this way. The arrow is a little bit bigger because we're closer. Over here, it's even bigger, even longer, and so on. Over there, it's that way. Up here, it's pointing like that. It's pointing that way. Not a great angle there. Over here, it's sort of pointing that way. And so different places we have different angles. So again, it looks like a very complicated calculation. Let's get a sense of the dAs. The dAs are normal to the surface, so normal means that way. Here it's something like that. Over here it's like that. And here it's kind of aligned. And here as well, it looks like it's aligned. But over here, it's no longer aligned. So E dot dA at each point looks like a difficult thing to evaluate. But of course, again, Gauss's law comes to the rescue because the integral of the electric field over the 6 sides of the cube is equivalent to the integral of the electric field over a closed surface. And so Gauss's law applies, and Gauss's law says, just look in. Don't worry about the electric field dotted into the surface elements. Just look inside and see how much charge you have. And when you do that, in this case, we of course get that there's Q naught, and so it must be true that the electric flux through the cube in this case is Q naught over epsilon naught. That's non-zero. And if we look, we can get a sense of this calculation not giving us zero simply from looking at the red electric field lines going through the surface. There's a net outwards number of electric field lines, if you will, coming out, unlike in the situation where we had here, we had field lines coming in and field lines coming out, therefore the possibility of a balance in some sense. Whereas here you don't have that. The electric field lines are definitely only coming out of the cube. And so there's a positive flux.